Feel free to ask me any questions while we wait. Got a couple minutes before class is supposed to start. I think Ethan's the one that just came in. Just letting you know, go ahead and ask me any questions if you have them. We still got about another minute before class starts. All right. So I don't have that many people in here, but I guess we should go ahead and get started. When we last met, we were talking about chapter 20, and specifically, I told you guys you wanted to go through chapter 20 and look at all the versions of the second law of thermodynamics. It's also going to mention, maybe it was in a previous chapter, but maybe it was this one, I can't remember. A zeroth law of thermodynamics is one that you should know, even though I didn't put it in. I didn't mention it. Let's put it that way. So you do need to know the zeroth law of thermodynamics, and there's also a third law of thermodynamics that is mentioned in chapter 20. So make sure I want you to make sure you look those up as well, and all the versions, of course, of the second law of thermodynamics that's listed in chapter 20. So I'll type that up in a in a message to everyone, just so you'll know. So I'm going to write all of them. And I see your question, Bruce. Yes, I will look at that. Was that your face-to-face test or your online test or just your practice test? Okay. There was some problems with those. I might have to reopen it and give you guys another chance because for some reason it just stopped working. So if it said 55, that means you missed 45 points of what's supposed to be in there. Even though you got them all right, it's just the system didn't show you the questions, so that's the problem. I'm typing in a message right now to let everybody know in the chat box, basically something that I want you to make sure y'all have for the next test. There's an online test that's due Monday night, the 17th at 11:59 p.m. The practice test is already up as well. but it covers chapters 19 and 20, and of course, all of them are comprehensive, so that means it covers 17 and 18. And it's going to be more advanced on what chapter 20 is about than the actual face-to-face test when we cover chapter 20. When we cover chapter 20 in the face-to-face test, it's going to be that simple stuff I told you. But the online test is sort of like the homework. So I'm allowing you to do a little bit more because you're allowed, to look up stuff. So it's a learning experience for you. So make sure you know. Uh, okay, so I just finished typing. It was coming in here. I just finished typing a chat of the laws that you need to make sure you know for basically for the rest of the tests. So some of this includes information from the first semester. So you definitely need to know for Newton's first, second, and third law. And when I say Newton's first, second, and third law, or Kepler's, or the law of thermodynamics, or something like that, not only do you have to know the law, but you have to know which one's the first, which one's the second, which one's the third. So you need to know Newton's first, second, and third laws of motion, Newton's law of gravity, Kepler's first, second, and third law of planetary motion. You need to know conservation of momentum and under what circumstances that's valid. And you also need to know conservation of angular momentum and under what circumstances that's valid. You also need to know the zeroth, first, second, and third law of thermodynamics, and specifically every version of the second law of thermodynamics given in chapter 20. So that means you need to know not only the second law of thermodynamics is listed in chapter 20, but each one, like one's the Kelvin Planck statement, another one's the Clausius statement. So you need to know the names of those. So I'll put that now in the chat so you guys can go ahead and copy that. But that's definitely something you need to know. Let me go ahead and mark off these other students that came in. I got that one. And, oh yeah, I got this one too. Okay. All right, so I've got the roll. Anybody have any questions on that? So yeah, I'll check Bruce on your test. Anybody else has any problems like that, let me know. I might, if it's since it's actually an online test as opposed to a practice test, I will definitely give you the full 100 for it. But you're kind of, it messed you up by not being able to see enough questions to get the full 100 points. So it sort of was counterproductive for you. So I'm inclined to let y'all open it back up and give you two more chances, just so you can study it again. So keep an eye on that. But yeah, you automatically got your 100. So even if I open it, you don't have to do it. But be aware that that would be to your advantage to do it, just because you get more opportunities to see the questions that are related to 17, 18, 19, and 20. Any other questions anyone has? Okay, so as I was saying, in chapter 20, we started off, and I gave you, for instance, the Clausius statement. of the second law of thermodynamics. Of course, we already knew the first law of thermodynamics is basically conservation of energy. And you should be able to recognize it in words like conservation of energy, or you should be able to recognize it in equation form, delta E internal equals Q minus W, or delta K plus delta U plus delta E internal equals Q minus W is another way of stating it. And the same thing is true about the second law of thermodynamics, equation forms and sentence forms, because basically what can often happen is I'll have a list of sentences that are labeled A, B, C, D, E, F, G, and then I'll have a list of laws that are listed 1, 2, 3, 4, 5, 6, 7, and you're going to match them quite often. So you want to be able to pick all those out. And I'll have some things that are completely made up or not laws at all, and some things that are laws. So they sound really good, but they're not related to the stuff we learned. So just keep that in mind. Those are things you should, upon leaving this course, 2-semester sequence, you should know all of those things I just wrote there. So keep that in mind. With regards to chapter 20, we already covered, for instance, the Clausius statement of the second law of thermodynamics, which states, and I've highlighted it in my version of the book, and I said share. So that should allow you guys, when you open your e-text in My Lab of Mastering, you should see some blue highlights. And those are the things that I've highlighted to make sure you know. So the second law of thermodynamics is a statement about which processes occur in nature and which do not. That's why your book introduced it. One statement due to R.J.E. Clausius, who lived from 1822 to 1888, is that heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. So that is the Clausius statement of the second law of thermodynamics. That's one of the versions you should know. I'm usually not so big on making you write it out verbatim, but memorizing it verbatim and then recognizing it, that's more important. So make sure you've read it a bunch of times, written it down a bunch of times, that sort of thing. After that, we go into a talk about heat engines. I'm going to give you a little bit of information on that today before we go on, and sign conventions for that. They're also going to talk a lot about steam engines and internal combustion engines. So they actually give you a lot of details about diesel engines versus gas engines and why the temperature difference is so critical and that sort of stuff. Then they talk about efficiency in the second law of thermodynamics. So I'm going to give you that result. I'm not going to derive it like I normally do. Your book derives it really well, and there's some easier ways to derive it. But the main thing is you need to know how to calculate efficiency of a heat engine. And that should be a fairly trivial calculation. Coefficient of performance for a cooling system is another thing you should be able to calculate. Again, just the most simplest cases, not anything super complicated. But your book goes through specifically the Carnot engine, and then it does a nice derivation for the Carnot engine. And according to a theorem stated by Carnot, all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have an efficiency less than this. That's known as Carnot's theorem. Okay. That's a predecessor to another version of the second law of thermodynamics. Basically, what Carnot did is found that here's a very special type of an engine, a Carnot engine, where it's reversible and adiabatic and all this good stuff, where you have very specific parts that are adiabatic, but the main thing is it's reversible, it's quasi-static, so it's really the best, most efficient engine you could possibly imagine. And that particular one, the Carnot engine, and several others are also equally efficient. But the main thing is, if you calculate the efficiency of the Carnot engine and you calculate the efficiency of a real engine, the real engine is never going to be as efficient as the Carnot engine. And that's the same thing for all those other engines, which, like I said, other textbooks actually cover a lot. There's a Stirling engine, there's a Otto engine, and a bunch of stuff like that. And there really are different versions. But the main thing is that you know that heat engines have something to do with the second law of thermodynamics. And here's that statement. So here's the second law of thermodynamics as given by the Kelvin-Planck statement. So I'm getting ready to read that to you guys. I went ahead. Oh,
No device is possible whose sole effect is to transform a given amount of heat completely into work. This is known as the Kelvin-Planck statement of the second law of thermodynamics.
okay.
Figure 26.
So evidently, I figured out a way unknowingly to make my book read to me. I did not know it had that ability. I actually I knew that it did. I just didn't. I just didn't necessarily know how to ignite it, so I got it started. But anyways, yeah, the second law of thermodynamics in the Kelvin-Planck statement is no device is possible whose sole effect is to transform a given amount of heat completely into work. So that's another version of the second law of thermodynamics. And the important thing that I want you to know here is all of these versions have been proven to be exactly equivalent. So one's no more valuable than the other. It's just in some cases one's really easy to apply to a particular problem, and in another case it won't be. So that's why we have so many different versions. But that's the Kelvin Planck statement of the second law of thermodynamics. I'm looking for another one. Oh, here's where it says the result is known as the third law of thermodynamics. I'm looking for that footnote that right here it is. A real irreversible process cannot be plotted on a PV diagram except approximately if it approaches an ideal reversible process. But a reversible process, since it is quasi-static series equilibrium states, can always be plotted on a PV diagram. A reversible process, when done in reverse, retraces the same path on a PV diagram. So that's the third law of thermodynamics.
A real, irreversible process cannot be plotted on a
Evidently, my right mouse button does that, and I didn't know it. So I'm going to highlight this down here. Oh, start audio here. I see. There's a little headphone in my mouse collection that sometimes comes on. And this one did not allow me to actually. I'm trying to make it share this one, but it's not letting me. So I'm highlighting both the footnote as well as, there it is, as well as the actual statement. A real irreversible process cannot be plotted on a PV diagram except approximately if it approaches an ideal reversible process. So that was a third law of thermodynamics, which I told you is one of the things you should know. Your book does cover the Otto OTTO cycle. That's what I was telling you about, is another one of the types of heat engines. I'm not going to have you calculate anything with that. It does cover refrigerators, air conditioners, and heat pumps. That's where you get the idea of a coefficient of performance. So that's another thing you should be able to use. Here's another second law of thermodynamics, which is equivalent to the Clausius statement. It says no device is possible whose sole effect is to transfer heat from one region at temperature TL into a second region at TH. So that is another version of second law of thermodynamics, which sounds just like the Clausius statement, and it is. So I just wanted to make sure that's listed. And I'm going to do highlight, and I'm going to do share note, and then I'm going to do highlight. Okay. Now I've gotten this other version, which again, like I said, it's just another statement of the Clausius statement. So it's a repeat. Now I'm looking, oh, it does cover the coefficient of performance. That's again still in the same section. I'm not seeing another version of statement of the second law of thermodynamics. Your book covers the SEER rating. Again, that's very interesting and something you should know about as a possible future homeowner or as a possible civil engineer or mechanical engineer. But you can pretty much ignore it. I'm not going to ask you any questions about it on the actual face-to-face test, and I don't think I put any. I tried to remove all of them from the online test. Now I'm going on to another one. Entropy is a state variable. That's something you should know, but that's not a statement of the second law of thermodynamics. And it's much like potential energy. However, one form of the third law of thermodynamics states that. Okay, I found another statement of the third law of thermodynamics. So I just highlighted that, and again, sharing the note. So you'll find that in the section on entropy, showing entropy as a state variable. Again, it's highlighted, so you shouldn't have any problems running into it and finding it. And almost done here. Here's the general statement, second law of thermodynamics. Highlight, share a note, and here it says the total entropy of any system plus that of its environment increases as a result of any natural process. So this is another version of second law of thermodynamics. It says the total entropy of any system plus that of its environment increases as a result of any natural process. So that's another version of second law of thermodynamics. They then talk about times arrow, which is really the only thing we have that correlates nicely with time is in fact entropy. So here's another general statement of the second law of thermodynamics. This one says natural processes tend to move toward a state of greater disorder. Natural processes tend to move toward a state of greater disorder. Again, I highlighted it so you don't have to rapidly try to copy it down or anything like that. Your book does talk about biological development because some people that aren't that knowledgeable or they're really dishonest or making claims like the second law of thermodynamics forbids the theory of evolution. So your book and author have taken the time to make sure they show you that's false. So that's what that section is about. Here is a important aspect of the second law of thermodynamics. Both examples illustrate an important aspect of the second law of thermodynamics. In any natural process, some energy becomes unavailable to do useful work. So that's basically where I was telling you that you can sort of think of heat as sort of a bastardized version of energy, a lower quality form of energy, or your book is saying energy is degraded. So whenever you turn energy into heat, some fraction of it's going to disappear, period. You can't do anything about it. I'd say it's disappearing. It's not, it's not violating conservation of energy. It's just no longer available to be used as mechanical energy anymore. It stays as heat. So basically, it went into heating something up, and you're not going to get that back now. And then it goes into statistical interpretation, and it talks specifically about what entropy is, and entropy turns out to be K times the natural log of W, which is a number of microstates corresponding to a given macro state. And I'll explain that with regards to basically parking. Let's see, this is another statement of the third law of thermodynamics. So let me go ahead and highlight that for you too.
It's not possible to reach absolute
There I
zero.
go again. Sorry about that, guys. So another way of stating the third law of thermodynamics is to say it's not possible to reach absolute zero in any finite number of processes. So that's a whole different version of conservation, or excuse me, of the third law of thermodynamics. Basically, it's impossible to reach 0 Kelvin. So that's one way of thinking about it. It's kind of nice. I like it. I just did that. Let's see. Oop. That was not what I meant. I want to put that back on now. Okay. Now I'm trying to highlight this, but it won't let me, so I just have to leave it at that. But notice there is a This last statement is one way to state the third law of thermodynamics. That part's highlighted and the other part's highlighted, but it won't let me share that one. So I don't know exactly what's going on or why it's doing it, but it definitely is not letting me do what I want to do. So that's kind of a pain. There it goes. Okay. Now, all right, I got both those done. And I think that's it. Let me double check, make sure there's nothing else. It talks about global warming and stuff of that sort. None of that brings up anything. Okay, so that's it. All right, so I'm now sorry for the boredom that just happened there. That was some of the worst teaching I've ever shown you done in my life. I just wanted to be thorough, so I wanted to give you a full accounting of it. So I went through and just read all the versions of the second and third law of thermodynamics as listed in chapter 20. They do talk about specifically chapter 20 dash or section 20-10. That's where the third law of thermodynamics is introduced. And then, like I said, there's two versions I just highlighted. So hopefully that will help you guys. As I said, the homework will be more involved and the online test will be less involved than the homework, but still more involved than the face-to-face test with regards to chapter 20. As I said, when you actually do the face-to-face test or any future face-to-face test that includes chapter 20, which could be any of them from here or from the next face-to-face test on, because they're all comprehensive, your goal is to make sure you know those laws that I typed in the chat. So make sure you copy those and to also be able to calculate the efficiency both of a Carnot engine as well as an equivalent heat engine and the coefficient of performance. That's pretty much all you have to be able to do for chapter 20 for me on the face-to-face tests. Okay. Now, with that in mind, I'd like to go back to the beginning of section chapter 20 and talk some more about the second law of thermodynamics, specifically reminding you what it is. So the example I gave you last time is a very typical one. So you imagine having a cup of coffee or a glass of tea or something like that. You said, could I type that second part of what we need to know? That's actually all stated in the paragraph right above it. Ava, do you see that paragraph where it says, because you came in when I was typing that, it says Newton's first, second, and third law of motion and Newton's law of gravity and so on and so forth. Do you see that list? Okay, let me retype that then just to make sure everybody's on the same page. So I'm going to put another chat up, the exact same one I just did. And I'm going to do this to everybody, not just to Ava. Okay, so that's the list of everything you need to know. Basically for the face-to-face part, the only additional part is calculate writing this too now. Okay, so there's the other part. So those things are really all you need. You're welcome, Ava. Those things are really all you need for the face-to-face test. Make sure you can do those three simple calculations I just showed you. I'm going to do an example of each in a second, so that'll help you as well. And then make sure you know those facts. And these can come up, like I said, the whole rest of the semester. Uh, all our tests are comprehensive, so I can, if I see, for instance, that several students didn't get the thermodynamic stuff, then I often put them on the next test. And if they still don't get them, I'll put them on the next test too. Not as a way to try to hurt people's grades, but as a way to say, hey, this is important. I need you to leave with this knowledge in your head. And if you don't have this knowledge, you're not doing yourself any kind of favor. So that's why I keep repeating it. So I just want to make sure you guys know that. So as I was saying, the second law of thermodynamics, we often use an example of like a cup of coffee sitting on a table. And if it were to be knocked over, it would hit the ground and shatter in a bunch of pieces and coffee would be laid everywhere and so on and so forth. And according to the first law of thermodynamics, that's valid. And in fact, according to the first law of thermodynamics, which again is just conservation of energy, it's not forbidden for all of the tea to come out of the floor that it landed in, regroup as little particles or drops of coffee, jump up into the place where the coffee cup was spilled as well as cracked, and then the parts of the coffee cup come together where they were cracked apart, and it reform into a coffee cup that's one solid piece and has the coffee in it, and in fact jumps back up onto the table. That is, none of that's violated by the first law of thermodynamics. However, we know that never ever happens. So what we've discovered is there's a quantity we call entropy, which is often synonymously used with the word disorder. Okay. So in general, processes go from a state of low order, or excuse me, high order to high disorder. That's the normal thing. And that variable we found trucks with reality and time. That's why we call it time zero. But that is one thing that we can say definitively changes in jumping the coffee cup jumping from the table to the floor and shattering, and then the reverse of that. In the on the way down, the entropy increases, but on the way up, when it reassembles itself, the entropy decreases, and therefore, according to the second law of thermodynamics, that's not going to happen. So that's the value of that. Another thing that's completely reasonable with regards to the first law of thermodynamics is you take, for instance, an ice cube at, let's say, negative 15 degrees Celsius, and you put it in an aluminum cup of water in a calorimeter, and the aluminum cup and the water itself are initially at 20 degrees Celsius, and you put in this ice into the cup of water, and what normally happens is the cup of water, it being warmer than negative 15 degrees Celsius, is immediately going to be taking heat from the water going into the actual ice to first bring the temperature of the ice up to 0 degrees Celsius, and then to melt it, and then to bring the ice up to the final temperature, which will be the equilibrium state for the water that was always water, the water that was formerly ice, and the aluminum cup. And the end of that might make the actual equilibrium temperature, let's say, be 18 degrees Celsius. Okay. So we stuck in a negative 15 degrees Celsius ice cube of a certain mass, you can pretend like you know it, and into a cup of water that was at 20 degrees Celsius, a certain mass, that's in an aluminum cup of a certain mass that was also at 20 degrees Celsius. And what ultimately happened is the ice melted and the whole thing reached an equilibrium temperature of 18 degrees Celsius. Now, that's consistent with the first law of thermodynamics, and it also happens to be consistent with the second law of thermodynamics. But this other version I'm getting ready to tell you is not consistent with the second law of thermodynamics, but is with the first. Now, imagine you have an 18 degrees Celsius cup of water that's in equilibrium with a aluminum cup and a calorimeter. Now, spontaneously, what could in principle happen is heat from some part of the water that's in the actual aluminum cup. Heat from that can choose to leave and bring that particular sample or portion of the water down to 0 degrees Celsius, while warming up the remaining water up closer to 20 degrees Celsius, and the aluminum cup up closer to 20 degrees Celsius. And then ultimately, once it gets that one particular volume or particular part of the water down to 0 degrees Celsius, it could spontaneously draw more heat from the existing water, instantaneously freeze at 0 degrees Celsius, and then more heat can be drawn until the frozen part now reaches a temperature of negative 15 degrees Celsius. And then the net result would be an ice cube at negative 15 degrees Celsius sitting in a cup of water at 20 degrees Celsius in equilibrium with an aluminum cup at 20 degrees Celsius. Okay, that could possibly happen according to the first law of thermodynamics. But when you actually, and this is one of the few calculations you can actually make, If you actually calculate the change in entropy for that situation, you will find that the entropy actually decreases in doing that reverse order thing. So that's why we know it doesn't happen. Anybody have any questions on that? Okay, so that's a good introduction to the second law of thermodynamics. I will tell you that one of the ways we can think of the second law of thermodynamics is uh, basically the second law of thermodynamics. One can be thought of in terms of heat being a lesser quantity of energy. So heat is low quality energy, whereas mechanical energy like kinetic energy, potential energy, rotational kinetic energy, translational kinetic energy, all that sort of stuff, those can readily be changed back and forth between kinetic and potential, and you don't lose any. But if by any chance in the process of some physical event taking place, if some of that heat is converted or some of that energy is converted to heat, maybe it's a pendulum rubbing against the surface like that. That pendulum rubbing against the surface is actually transferring energy to the surface via heat, and that heat, some fraction of it will be lost, period. No ifs, ands, or buts about it, meaning you're never going to get all that energy back. So that's another way of thinking about the second law of thermodynamics. But another way of thinking about the second law of thermodynamics is that disorder or entropy increases. So you've probably noticed, this is another often used example. You've probably noticed how it's not very easy necessarily to pull into a parking space. I know for a fact there's a ton of students at TCC that don't know how to pull into a parking space. I've had my car hit like 4 times uh, while working there. So it's just a freak of nature. Not only that, I can't tell you how many times I pull get ready to go into a parking space where someone's completely gone over my side of the line or parked diagonally or something like that. But either way, evidently it's a little bit harder to park in a parking space than it is to pull out of a parking space. And what I'm telling you is the second law of thermodynamics can help us understand that. So let me draw a version of a parking space for the second law of thermodynamics. And notice me, being the excellent teacher that I am, I'm actually remembering to share my screen with you before I start writing on my iPad. I literally made a bunch of mistakes of that in the last few days, so I'm acting like I'm really good and never do that. It's just a fun thing I like to pretend sometimes. All right. So, what I want you to think about is a parking space. So, let's imagine your parking space looks like this. And let's say it also looks like this. And let's say it also looks like this. So these are the two lines for your parking space, basically, is what I'm trying to say here. Oops. That one did not turn out very well. Okay, good enough. All right, now what I'm going to do is I'm going to draw a car. Okay, so that's a car. Now you can imagine it's a car, but it might not be that obvious. But basically, you can take this thing. Let's do. I want to copy it. Let's see if it'll let me. No, of course not. Yeah. Well, what I was trying to do is ideally I'd like to copy it. But what you can imagine is how many different ways can you fit that little rectangle inside that parking space? So, as a simplest case scenario, you could say it's this all the way pulled to the front. That's one way. Then you can pull back another millimeter, and that would be another way, and another millimeter, and another millimeter, and another millimeter. And all these different ways are different ways you could pull into the parking space and still be validly parked, or at least parked in a way that would not be justified giving you a ticket. And of course, you can also park in all these different ways too. So, and I'm just showing a small fraction. Now you can also park right up against this line right here, and then all the way over to here, like that. And then, of course, you can do just a millimeter over, and another millimeter over, and another millimeter over. And you can keep doing that, of course, until you get all the space covered up over here. So I think you see there is really a lot of different ways in which you can park and still be in that parking space, right? So that means there's a ton of micro states in the one macro state that we call parking. Okay. And I haven't even covered the cases of where you could actually park diagonally. So you could actually have your car parked like this. Ideally, it'd have to be inside. So there are ways of doing that. That's why it would have been nice for me to actually be able to copy it. But the main thing is there's a ton of ways that you can fit in this parking space. And you could even argue that there's an infinity of ways because there's no smallest measurement that you can move to the left from the first parking space. There's no smallest measurement that you can move forward from the first parking space. There's no measurement, smallest measurement where you can move to the right of the initial parking that I did, or to the back. So each one of those gives you an infinity. Then you could do it again for another little bit further back, a little bit further back until it's all reached the very front where you've parked all the way against the front edge of the parking space, or all the way back to where the back edge is lined up with the back edge of the parking space. All of those make an infinity of parking spaces or parking positions that are valued. Okay. So you've got left, right, forward, and backwards. You also could then start doing diagonals. Long as you keep them between the lines, they would be valid as well. And there's a lot fewer of those, but still it could be in some sense an infinity of them. So you can see that there's a lot of micro states corresponding to the macro state of parking. But if you look at when you go to pull out of the parking space, notice you pull out like this, and that's a valid space. That's a valid place. That's a valid place. You can see there's, in fact, way more parking or way more spaces available to you outside of the parking space than there is inside of the parking space. So you're actually going from a place where inside the parking space, there are very many microstates in the macro state called parked. Okay. But out here, there are, and I'm using exponentially in quotation marks here because it's actually probably even more than exponentially. But I'm just trying to say it's a really huge factor larger, exponentially more positions. I should say positions of the car. So there are exponentially more positions of the car in the non-parked macro state. Since S equals entropy, which is sort of equal to disorder, and S is equal to K ln W, which is the number of microstates, in the macro state. Actually, both of those words were too big to fit in where I did them, so I'm going to write that. So number of darn it. In the macro state. So you can see S equals K ln W is big. For parked, but S for non-parked is way, 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 way bigger than S parked because of the way many more microstates. Okay. So that's another way of thinking about why is it easy to pull out of a parking space versus relatively difficult to pull into a parking space. And you can think of that as because there's so many different ways you can pull out of a parking space that are all valid. And that in many ways is huge, even compared to the many ways you can park in a parking space. So because of that, the entropy actually goes up when you pull out of a parking space, and that's more like a natural process and therefore easy. Anybody have any questions on that one? So that's like another description of the second law of thermodynamics using the idea of entropy. Okay. And your book does a really good job explaining that S equals K ln W uh, for specifically like coin tosses and stuff like that. When you're dealing with that kind of a system, it's a lot easier to work with coins and stuff like that. And you can actually do calculations with it. If you want to apply this formula in general, you have to do what we call statistical mechanics, or they also call it statistical thermodynamics, where you're literally counting all the ways that particular atoms can be in particular states with particular energy and all that good stuff. It's a way more advanced topic, not something that you can cover in a sophomore or freshman level physics class. But just know that if you go far enough, there are ways for you to do these things, and that's what physicists have done. That's, for instance, how Maxwell got his Maxwell distribution that we use to find the most probable, uh, the average of V, the average of the square of V, and so on and so forth. Any questions on that? All right, so what I want to do next is I want to go ahead and give you an idea what a heat engine is. So what is a heat engine? So a heat engine is it's a thing, but it's also a process. And then you can actually take the process that you contrive in your head and make a physical thing out of it. And then that thing is potentially an engine for a car or for a train or for an aircraft or something like that. But at the lowest level, you can sort of think of it as this way. You can say there is, in fact, a high temperature reservoir and this is a reservoir at temperature TH. And then there's a low temperature reservoir and that's at temperature T low. Okay. Now, when we think of the heat engine, we sort of picture it as this big circle in the middle. Okay. And now I'm going to draw it with a better circle. Okay, so there's our heat engine. I'm going to pull it up a little ways, make it a little more centered up. Okay. And what we have to imagine is some heat must be taken from the environment in some way. Now, if you're talking about a gas engine for a car, for instance, the environment would include the gas station where you got gasoline, and then it was stored in your car as part of the system for a long period of time. And then all of a sudden, the piston and the fuel injector calls that actual gas into the chamber, the piston chamber. It'll be atomized, so it's basically a gas. It'll be mixed with air at some ratio, and it'll be at some specific temperature. So this gas coming in could be thought of as the heat coming in as well. More specifically, as the piston starts to compress it, and then the spark plug fires on a gas engine, not a diesel engine, then there's actually a high temperature explosion that occurs inside of there, and that produces heat. And what we're trying to show you with this diagram is that basically there is a flow. Actually, I don't think I want to do it there. I think I want to do it here. There is a flow of heat QH into the heat engine, and then the heat engine is going to basically make some of that heat go into actually usable work. So out this side goes work. And because it's coming in as heat, and I told you heat is a bastardized form of energy, you can't use all of it to do work. So some of it's going to be wasted. And in fact, what's going to happen is the amount of heat that is wasted is going to be Q low, and that's going to be dumped into the low temperature environment, which would be out the exhaust. Okay. So that is what a heat engine is and what it does. Okay. Now, the way we define efficiency is we use a symbol like this. That's the efficiency. And it's basically what you get divided by what you pay for. Now, what you get, I might also say useful. In other words, what do you get that's actually useful? That's the W. And then what we're going to do from there is we see that basically QH has got to equal W plus QL. That's just conservation of energy. So conservation of energy implies that the total heat coming in has got to be equal to the work done plus the total heat going out, QL. And that is basically our parts of the heat engine. Now, when I will go to calculate the actual efficiency, I've got to use those particular variables to come up with it. I'm actually checking right now. I was using a different book, so I will say another symbol for efficiency. Sorry, I've been using a book where the eta that I just drew there, that N looking thing, was the efficiency, but I misremembered. Your book is actually using E for it. So the E or the eta could be the efficiency. So for this heat engine, efficiency E of this heat engine is E is equal to, what you get is what's useful. So that's the W. And what you pay for is the whole QH. Okay, all that energy coming in. Now, that's pretty big, but you can also use this little guy, this equation that I got from conservation of energy. That will tell us that W is equal to QH minus QL. So now we can say QH minus QL over QH, which you can interpret as QH over QH minus QL over QH. And in fact, that is 1 minus QL over QH. So the efficiency of any heat engine is 1 minus QL over QH. It's also work divided by QH. And I think those are the most valuable forms, but one other one that might be valuable is QH minus QL over QH. So those are the most important forms of the efficiency for any heat engine. So any heat engine has these efficiency. Any questions on that? All right, so let's do an example. I think I pulled too many pages. Okay. Example 1. A car has an efficiency of, let's say, 30.0% and produces 25,000 joules, which equals 25.0 kilojoules. In other words, I have 3 sig figs per second, kilojoules of work per second. A, how much heat input is required? And B, how much heat is wasted? And both of these are per second. I'll write here. Okay. So there's our problem to be solved. Now, what we know is the efficiency is work divided by QH, and that's equal to 0.300. Okay. What we know is a car has an efficiency of 30%, so we've got that, and produces 25.0 kilojoules. So that tells us which quantity is 25 kilojoules. Is it W? Is it QH? Or is it QL? Or is it E? Anyone? Let me open up my chat. It seems like my chat did not come up, just in case anybody else is asking questions. Anyone? All right, so the reading says a car has an efficiency of 30% and produces 25.0 kilojoules of work per second. So the work is what that is. So W is equal to 25.0 kilojoules. Okay. So we can now solve for QH by saying QH is actually going to be equal to W over the efficiency. Well, the work is 25.0 kilojoules per second, and the efficiency is 0.300. So if I take 25 divided by 0.3, oops, yeah, that's 83.33. That equals 83.33 kilojoules of heat added, or heat taken in. Whoa, no, per second. So we've got our answer to part A. Okay. Now, how much heat is wasted? QL equals heat wasted. But remember, QH is equal to W plus QL. So QL is actually equal to QH minus W. So we can now say QL is equal to 25, or excuse me, 83.33 kilojoules minus 25.0 kilojoules. And that gives me 58.33 kilojoules of heat wasted per second. Any questions on that? Now, there's other ways you could have done it. For instance, you could have said, I'll just write this as alternative. We could have said E is equal to W over QH, which would also allow us to say W is, of course, QH minus QL over QH, which equals 1 minus QL over QH. Then from that, you could say QL over QH is equal to 1 minus E. Then you could say QL is equal to QH times 1 minus E. And that would be, of course, 25.0, or excuse me, this is the 83 again. This will be 83.33 kilojoules times 1 minus 0.300. That's 83.33 times 0.7. which should give you the same answer. And sure enough, it does 58.33 kilojoules. So that's another way you can do it as well. Any questions on that? Okay, I'm trying to look, see if I missed anybody. I don't know. Let's say I got everybody. All right, so that's a simple problem dealing with a heat engine and specifically the efficiency of it. Your book then talks about the Carnot engine. So I'd like to give you a rough estimate of what the Carnot engine is. So a Carnot engine is supposed to be like a heat engine in that it has steps and phases that we're knowing. But what we're doing is we're imagining it taking place so slowly that it's a string of equilibrium points that are connected by a infinitesimal stretch in time and space. So, for instance, this itty bitty movement from one point on a P versus V diagram to another point, that's just infinitesimally small, and both the initial point and the final point are equilibrium points. And in fact, it's so close that you could immediately reverse it and it would go right back to where it was. That makes it reversible. So it's quasi-static, it's reversible, and in fact, we're ignoring friction, all sorts of good stuff. So let me show you with a P versus V diagram what we mean by the Carnot engine. So here's our graph, and this is going to be the pressure, and this is going to be the volume. And what you're going to imagine is there's going to be a point in space, let's say right here, and this is in the phase space, if you will. That's actually an isotherm. So we're going to have an isotherm that comes like that. And then there's going to be another isotherm, a lower temperature isotherm, like that. And what we're going to do is we're going to go from this point here, which, dang it, which I'm going to call A. I'm going to go down here along that isotherm to point B. And while that happens, a certain amount of heat, QH, is going to flow in. And then there's going to be an adiabatic expansion from here to here, which would be point C. I'll draw a little arrow there. I'll draw a little arrow there. This part is an isothermal process. And that's going to be isothermal at TH. And this part is going to be an adiabatic process. Like that. And it's going to go from B to C. Then I'm going to go back. Oops, wrong color. Then I'm going to go back to here, which would be point D. And of course, that's an isothermal process, followed by a adiabatic process. So this one's going to be isothermal at T low. And in fact, at that point, we're going to get a heat QL flowing out of it. And then finally, this part right here is going to be adiabatic. So that's what the Carnot engine is. It's an isothermal process at a constant temperature TH where amount of heat QH is entered. And then it's going to be an adiabatic process where it goes from a temperature TH to a temperature TL by a thermal expansion or by an expansion in general. and then it's going to compress. And when it compresses, it's going to give off an amount of heat QL into a reservoir at temperature TL to the point D. And then there's going to be an adiabatic process from D back to A. The nature of it being cyclic is what makes it a heat engine. So since you start back at the same state, you can do it again and again and again, and that's basically what's going on. So you can sort of imagine as A to B is the piston when the gas comes in, and the piston actually expands, the size of the cylinder gets bigger because the piston pulls back from it and opens the volume up. That low pressure can sort of be thought of as sucking the fuel air mixture in, and then it's going to continue to expand a little bit more in the adiabatic process. And at that point, you can then imagine it starting to do an isothermal compression from C to D, and then an adiabatic compression from D to A. So that's the way you can look at it, and that's actually the Carnot engine, and it's reversible, and it's well, it's basically, like I said, one of the most efficient forms of a heat engine as you can possibly have. Okay, now we know that the efficiency E for the Carnot is equal to 1 minus QL over QH. That's because it's true for all heat engines. Okay. Now, the other thing to realize is that if it's a reversible process, then something else is kind of nice. Reversible process implies delta S, the change in entropy, equals 0. So that's sort of the beauty of the reversible process, which the reversibleness of it and all that good stuff, that is where the non-friction and all that stuff comes in. Because if you had any non-friction, or if you had friction, it wouldn't be reversible, because you'd go from an equilibrium state and an infinitesimal distance to another equilibrium state. If that infinitesimal distance was across a frictionful process, then you'd lose some energy. So if you tried to go back, you'd actually go back to a different state. So it's not reversible. Now, we can work all this out like your book does, and your book does a great little calculation for it. I shouldn't say little, it does a great calculation for it using the fact that it's isothermal and all that good stuff to calculate QH and QL. But we can start right from here and realize that S in general is defined to be delta S is equal to delta, well, you can call it delta Q. We normally say dq over t. So what you can interpret here is qh over th is equal to ql over tl, because that's the definition of entropy, right? So from that, we can reach the conclusion that ql over qh is actually equal to TL over TH, which gives us E Carnot is equal to 1 minus T low over T high. And that's the actual Carnot efficiency that you need to be able to use. And I will repeat the statement according to the theorem stated by Carnot. All reversible engines operating between the same two constant temperatures, TL and TH, have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have an efficiency less than this. That's known as Carnot's theorem. So let's look at another example. A steam engine operates between 600.0 degrees Celsius and let's say 250.0 degrees Celsius. What is the maximum possible efficiency? Oops. So one thing I got to point out here is with entropy and with the efficiency, if you're using the temperature, it's got to be in Kelvin. We're using, in fact, I didn't show it to you, but in general, the units of the entropy has to be joules per Kelvin. Okay, so you can't put those temperatures in unless they're Kelvin. So I'm going to say TH is equal to 600 plus 273. That's 873 point, is actually technically point 2 Kelvin. And T low is 273 plus 250. That'd be 620. 620.2 Kelvin. Okay, so that's his two temperatures. So what we want to do is figure out the Carnot efficiency, because the Carnot efficiency is the most efficient engine possible between any two temperatures. Now, of course, you could also find other ones, but Carnot is what we're working with. So I'll use the Carnot efficiency, which equals 1 minus TL over TH, which equals 1 minus 620 or 623. Sorry about that. Let me fix that too. I'm adding 273.15, which would be 273.2 to it. So when I add 273 to 250, I should get 623.2 Kelvin. So that's what I'm going to put there. So 623.2 Kelvin over 873.2 Kelvin. So 1 minus parentheses 623.2 divided by 873.2 close parentheses. That gives me 0.2863. So the efficiency max is the efficiency of the Carnot engine, which equals about 28. Now I need to look at how many sig figs 623.3 over 873.2 had. So 623.2, sorry, I said 0.3, divided by 873.2. That gave me 0.713. One is to any number of sig figs. That's 4. So I should actually have 4 decimal places. So that's actually right. And this should have been 303. So these two are not sig figs. So I'm going to call this 28.6303%. Does that make sense? Yes. Thank you for catching that. I was rounding it. Wait a second. Yeah, it would be 522. Okay. Thank you for catching my mistake. I think that was Ethan. Thank you, Ethan. Feel free to speak up, by the way. I'm going to say no. I'm going to say no. I'm going to say no. Okay. Now, what it actually turns out to be is 523. Let's do 523.2 divided by 873.2. That's 59.9% roughly. So actually, the result is not the 28.63 that I had told you about. It's going to be, now that I've corrected it, it's going to be, whoa, Nelly. The Carnot efficiency is going to be 40.00, oh, 0.08. I can make that an 8 pretty easily though. Maybe not that easily. Okay, 40.08, and the next digit is 2, and that's an extra digit. So 40.082 is the efficiency with the correct numbers. But yeah, thanks for catching me on that, Ethan. I appreciate it. Yeah, I rounded up twice. I rounded up for the 50 plus the 73, and then I rounded again to 60. So that's why I screwed up. It's a complete bonehead thing. Anyways, anyone have any questions about that? All right, let's go ahead and take a let's take a 7-minute break. So come back at 6:55, and we'll finish off what I need you to be able to do in this chapter, and then we'll probably go into chapter 21, but I'm not sure because it's really a lot to jump into. Okay. So go ahead and I'll let you know I'm going to be here the whole time, but you're supposed to come back at 7:50, excuse me, 6:55. About 2 more minutes. Anybody have any questions, feel free to ask them. All right, I guess it's about time to start back up. I went ahead and wrote the Carnot engine across the top of that diagram and explained that it's reversible. And that means it's a series of equilibrium states separated from one another by infinitesimal changes in the variables. By doing that, you can always reverse it. That's what makes it reversible. And the fact that it's reversible means that if you go ahead to one of those equilibrium states and you want to get back to the other state, you just reverse it, and you'll end up going right back through the same line. That's what makes it reversible. The fact that it's reversible tells us that the entropy doesn't change, which allowed me that really quick and dirty shortcut by saying that S when the heat was being added was equal to S when the heat was being lost. So I got QH over TH equals QL over TL. That allowed me to replace QL over QH with TL over TH for the Carnot efficiency. And that's the equation you need to be able to use. I wanted to show you another example of using efficiency and the Carnot efficiency. And this is very much like your example 20-3 in your book, where it says a phony claim. So an entrepreneur says their engine that they're wanting you to invest in, obviously, takes a 12.0 kilojoule, takes in 12.0 kilojoules per second at 450 Kelvin and puts out 5 kilojoules per second at 300 Kelvin. Do you believe these claims? Well, what would make me not believe them is if the thing was as efficient as a Carnot engine, or probably even close to as efficient as a Carnot engine. But the main thing is, if we found it was as efficient or even more efficient than a Carnot engine, we know he's lying. Okay, he or she is lying. So that's what we're going to do, is we're going to calculate the engine's efficiency. So for any heat engine, the engine efficiency is 1 minus Q low over Q hot, and that would be 1 minus. Now the Q low was the 5.00 kilojoules taken in at 300 Kelvin, and the Q hot is the 12.0 kilojoules taken in at 450 Kelvin. So we're going to get 5 divided by 12 gives us 0.416. That's 3 sig figs divided by 3 sig sigs. So we get 3 decimal places. And then I do 1 minus that. And that gives me 0.5833. So this gives me 0.58333 is the efficiency of this engine. Now the Carnot efficiency, E Carnot, is 1 minus T low over T hot. So that's 1 minus, now the low temperature is 300.0 Kelvin. We were lucky in that they gave us the temperature in Kelvin already, so Mr. Younger don't have to do arithmetic. And I'm going to divide that by 450.0 Kelvin. So 300 divided by 450 gives me 0.6666. When I subtract that from 1, that's going to give me 0.33333. So the engine efficiency equals 58.33%, and the equivalent Carnot engine has an efficiency of 33.33%. So we'd say no, this claim is a bologna sandwich. Any questions on that? Yeah, if you've ever found the second law of thermodynamics violated, either you're getting ready to win a Nobel Prize or someone's lied or you've screwed up. Okay. You will definitely win a Nobel Prize if you find the second law of thermodynamics is being violated in any way. It's so bad that we've gotten to the point where if we ever find something that looks like the second law of thermodynamics might actually be violated, we first look for an alternative form of energy that we never knew existed. Okay. And if we don't find that, then we'd have to go ahead and reach the conclusion that we have to throw away the second law of thermodynamics, or at least codify under what circumstances the second law of thermodynamics is really a law of thermodynamics as opposed to something that only works a lot of times. Again, a law is still something that works all the time, basically. But anyways, that's the way it is in the current state of physics. So if you ever find something violating second law of thermodynamics, unless you are really on some avant-garde research and you've really crossed all your T's and dotted all your I's and all that good stuff, then you probably made a mistake. Otherwise, you're in for a no bet. Anybody have any questions on that? Now, the Kelvin-Planck statement, I want to tell you just as another point, so you can have some idea visually what goes on with a heat engine. So when we talk about the Kelvin-Planck statement, God darn it. I can't believe I spelled Planck without a C in it. Like I haven't known that name forever. So here's a nice diagram that helps you understand the Kelvin-Planck statement. So let's take a heat reservoir right here of temperature TH, and let's take a heat engine right here. Let's allow some heat to flow into it. That heat is going to be QH. And then let's allow work to come out of it, and then nothing. So, in other words, no heat is wasted. So if you see a heat engine diagram like that, where they don't have an extra little bit of piping that goes down for heat to leave the heat engine and go into a cold reservoir, then you know it's not possible, because you can't turn 100% of the heat into work, period. No way, no ifs, no whats, no buts, no cuts, no butts, all that good stuff. Yeah, I just ran off on a crazy tirade of mixed metaphors. So, anyways, that's another version of the second law of thermodynamics, which says no device is possible whose sole effect is to transform a given amount of heat completely into work. There's no way, once you've converted some amount of energy into heat, let's say 1,000 kilojoules, you cannot get 1,000 kilojoules back out, period. No way. Okay. That's just sort of the fundamental idea that heat is a less quality version. So, any questions on that one? All right. So, the other thing that I want to talk about is I want you guys to understand about the coefficient of performance and refrigerators and air conditioners, mainly because I don't want you to be completely clueless about the first law, or excuse me, the second law of thermodynamics, which says that heat cannot flow spontaneously from a hot object to a cold object, or excuse me, from a cold object to a hot object. Heat cannot flow from a cold object to a hot object spontaneously. Now, if you think about a refrigerator, you have inside your refrigerator a cool area because your cheese isn't going bad, your mayonnaise isn't going bad, that sort of stuff. And you've got it plugged into a light receptacle, and there's a compressor in there and all sorts of stuff, electricity, all sorts of stuff is going into it. So we know it's using some energy. But what's really happening is constantly the heat from the environment, specifically in the kitchen and everywhere else in the house, that heat is penetrating through the walls of the refrigerator, which is insulated, but it can't be 100% insulated. So the air around the refrigerator is constantly trying to heat up the temperature inside the refrigerator, and therefore make the food go bad, that sort of thing. But your refrigerator is taking heat out of that cold environment inside the refrigerator and expelling it into the warm environment of the kitchen. And in fact, it makes your kitchen a little hotter, right? So, for instance, in the summer when everything's hot, the refrigerator is actually making that worse. Okay. Now, that is not a violation of the second law of thermodynamics because this did not happen spontaneously. In order for this to happen, you actually have to have a compressor doing some work and some electrical energy coming in, some fraction of which is being wasted. But the main thing is because of that, you can force the cool air inside to give up heat to the hot air outside. And you can imagine all you have to do, for instance, is let's say take a liquid or a gas and compress it. It's going to be warm. And then you run that warm gas through that cold environment inside your refrigerator. And basically what's going to happen is some of that heat. Well, actually, I want to do it the other way. Yeah. So let's imagine taking a gas, and instead of compressing it, let's take the gas and expand it. So gas is being pumped into a compressor, which is like a cylinder, and then the piston head is lifting up. That causes it to be a lower pressure. That cools down the gas, and then that gas is released into some metal piping, and that metal piping runs through the back of your refrigerator and freezer. Now the cold air inside of the refrigerator is actually warmer than the pipes that are behind the refrigerator and freezer, and therefore heat is flowing from the warmer air inside the refrigerator to the colder metal pipes, heating that gas back up. That gas comes back to the compressor, heated up, and then the compressor can re-expand it and all that stuff. That's what's going on. That's the same thing that's going on with regards to your air conditioner, where you're actually pulling heat out of the cold 70-ish temperature inside the house and expelling it to the hot 90-ish degree mark outside. So that's all things that are actually allowed, but they're allowed because they're not spontaneous. They have to be assisted. And you know that because you're paying a power bill for it and buying a refrigerator and all that good stuff. So it turns out the diagram for an actual refrigerator or heat pump, you can actually imagine it like this. So you have a hot reservoir of temperature TH, and then you have a cold reservoir of temperature TL. Okay. This reservoir in here, for instance, is inside the house or refrigerator. And this is outside / kitchen, assuming you have your refrigerator in the kitchen. Okay. Now we'll again draw a nice little circle to represent our reverse heat engine, which is really what a refrigerator air conditioner is. And what we're going to see here is we're going to have a pipe that actually can pull heat. And in this case, the heat is Q low is going to be pulled in. And then this heat is going to continue up like so. And in order for that to happen, something has to put some work in. So I'm going to put work right here and show work coming in. And then out back here is going to flow a heat, QH. Okay. So that's what a refrigerator or heat pump is. Actually, I'll say refrigerator or air conditioner. A little bit of difference there. So I'm going to say refrigerator or air conditioner, AC. Okay. Now, if we're talking about this, then we're going to do something that's not the efficiency. We're going to use something called the coefficient of performance. And I highly recommend you go out to Lowe's or Home Depot and look at their air conditioners and refrigerators, and you'll see that they actually have a coefficient of performance, which is called COP. And what that is what you get divided by what you pay for again. So it's the same little paradigm I'm using before, but what you get is the amount of heat pulled out of the cold environment. So that's going to be QL over what you pay for, which is the W that you have to put in. So that is the coefficient of performance that we're going to be able to calculate, and that I want you guys to be able to calculate. Now, you can see from this that conservation of energy dictates, and when I say conservation of energy, I want you to think first law of thermodynamics. That tells us that basically QL plus W is equal to QH. And because of that, you can say that W is equal to QH minus QL. So we can go ahead and say that the coefficient of performance is equal to QL over W, but it's also equal to QL over QH minus QL. And if you take a Carnot version, then you get COP Carnot is equal to TL over TH minus TL. So that's sort of the equivalent of the Carnot. In other words, that's the most efficient you could possibly get for a coefficient of performance. And if you find that your coefficient of performance is higher than what the Carnot would be, then you know it's BS or bologna sandwich. Okay. So let's look at an example. This will be example 4, I think. Yes. So example 4, a freezer unit, oops, has a coefficient of performance of 3.0 and uses 300 watts of power. How long would it take to freeze 600 grams of water at 0.0 degrees Celsius? So that's how much heat we're able to actually take out, is what they're really asking there. So we have our variables. Now what we need to realize is that to calculate this, we need enough heat to be pulled out of the freezer so that the ice can go from 0 degrees Celsius to 0 degrees Celsius. Excuse me, the water can go from 0 degrees Celsius in liquid state to 0 degrees Celsius in the solid state, which means we got to do the heat of fusion. And that is QL has got to equal the mass of the ice, or excuse me, of the water, times the heat of fusion of the water, which is equal to zero. I'm going to use kilograms, so I'm going to say 0.600 kilograms. I'm assuming all three of those digits were sig figs, times 333. That's the heat of fusion, is 333 kilojoules per kilogram. Okay, so that's what that is. And yep, got that. That equals 0.6 times 333 gives me 199.8. Darn it. Kilojoules. Okay. So that's how much energy came out. That's with one extra sig fig. That's how much energy we got to extract from the 0 degree water to force it to freeze. Now we know an actual amount of heat per second because it says it uses 200 watts. So using 200 watts means 200 joules every second. And we just need to figure out how many seconds it takes, and then that can help us. So what we know is power is equal to work divided by time. So time is equal to work divided by power. Okay. So what I'm going to do is I have to figure out a relationship between work and this power stuff to figure out how much energy I can get out. So it's using 300 watts of power. That's the actual W. And I know that the COP is QL over W. So I also know COP is equal to QL over W, so that the actual QL that comes out is equal to W times COP. I think I got that right. Let's see. Yeah, that would be for QL, but I don't want QL. I want W. That's what it was. Sorry about that. So I know that, yeah, I know the W, so that's okay. And what I'm going to do is I'm going to say the actual W is equal to QL over COP. So I can do that. That will allow me to take into account the efficiency of the actual freezer unit that I have, because dividing the QL by COP tells me what fraction of it actually becomes work take or energy taken out. So T is going to be QL over COP divided by the power. And the QL, of course, is the 199 0.8, and I should make that an actual times 10 to the third joules divided by 3.0 is the coefficient of performance. And all that is going to be divided by the power, which was the 200 joules per second. 300, excuse me, 300 joules per second. Again, treating that as if it's 3 sig figs. So I'm going to do 199.8 divided by parentheses 3 times 300, close parentheses. That gives me 0.22. 0.22. I think that's it. 198 divided by 3. I did that. Divided by 300. I did that. So 0.222 seconds is what that comes out to be. So it should actually do it really, really quickly. I didn't expect that answer to be that small, though. Let's see. 300 joules per second. That is the joules. 199.8. That looks good. And that's kilojoules per kilogram. So that's all looking good. Oh, I know. I wrote down the 10 to the third, but I didn't actually put in the 10 to the third. I actually just wrote it as 199.8. So let me redo that. It's 199.8 e to the third divided by parentheses 3 times 300, close parentheses. Now that gives me 222 seconds. That makes much more sense. I was like, it shouldn't be that small. That gives me 222 seconds, which 3 minutes is 180 seconds. So that would give me 2 minutes and 42 seconds. So that's pretty fast to go ahead and freeze, make ice out of a 600 grams of water. Anybody have any questions on that? So that's about the extent of it. You can look, there's other examples. For instance, they do an example on a heat pump, which uses a coefficient of performance as well. So you can figure out how to do that. These are really just pretty straightforward problems, and you'll see when you start doing the practice tests for online tests too, you'll see that these are pretty much straight plug and chug problems. There's not a whole lot of mystery in what's what. You sometimes have to think a little bit to figure out which is QH or which is TH versus which is QL versus TL, that kind of thing. But other than that, you really don't have to do too much. They're very straightforward problems, and that's what I plan on asking you in a teaching type situation or in a testing type situation, especially the face-to-face tests are going to be the easiest of the easy. Section 20-4-1 is where they talk about the SEER rating, and the SEER rating is heat removed in BTU divided by electrical input in watt hours. So that's just a fairly esoteric quantity that's used in the industry. But if you're going to become a mechanical engineer or probably a civil engineer, there's going to be times where that kind of thing becomes relevant. It's not unlikely or not unheard of for a mechanical engineer to do the ventilation system for a commercial building or something like that. So that's something you got to keep in mind. But you can always come back to it in this particular book or any other book at a later time. Later on, it does say that when we start talking about entropy, it says the entropy is delta S is equal to Q over T. So I'll just mention that to you. This is the definition. And we used it earlier, except I took a little bit of liberties with it. But delta S is actually heat Q over T. And that's the actual quantity that'll show you that you can't, for instance, allow ice to melt in a cup of water and then let it go backwards. That's not going to happen because you'll find that the net entropy to the universe gets smaller when you do that. So it's not physically possible. So they'll show you that in example 20-7. So I definitely recommend you see that, but that's the entropy part. And I don't really think there's much use in going in all the details. I mean, there is, but if you become an engineer or a physicist or a chemist, you're going to have a thermodynamics course in all of those cases where you handle this over 2 semesters, and they'll go in a lot more detail. But I wanted to at least mention what entropy was, mention how it's worked out, mention how it relates to the second law of thermodynamics, and that's it. So we are essentially done with chapter 20-6, or excuse me, 20. Does anyone have any questions? Okay. Well, we're a little bit early, and I really don't have enough time to do everything I want to start into chapter 21. But I think I am going to just give us a little intro to chapter 21. So let me do that real quick, and then I'll let you guys go. I'm going to let you go even a little early, anyways, even though I'm starting into chapter 21. So chapter 21 starts with electric charge and the electric field. And specifically, what they're talking about here is electric charge. So when you've encountered this in your own life, let me kill this share screen stuff. When you've encountered electric charge in your own life, it's probably mostly been due to, for instance, you scuffing your feet on the rug in the winter. As I assume all of you have done that. Yes, you know, scuffed your feet on the carpet in the winter, and then go to touch a doorknob and it shocks you. That's static electricity. That's a charge that's built up on you. Now, what's going on there is, for instance, if you're wearing shoes, then your shoes normally have a rubber sole at the bottom. That rubber sole has more affinity for the electrons in the carpet than the molecules of the carpet have. So generally speaking, when you rub rubber on carpet, since the rubber has more electron affinity, the atoms or molecules in the rubber has more electron affinity than the atoms or molecules in the carpet. What happens is the atoms in the rubber of your shoes will steal the electrons. And that's really the only way you can ionize an atom, is by stealing electrons or adding electrons to it. Okay. You can't mess with the proton and the neutron of an atom very easily, but you can definitely strip off electrons and add electrons. So when you scuff your feet, in general, what happens in almost all cases is the rubber in your shoes is stealing electrons from the carpet, and therefore you are becoming a net negative charge. The charges exist as positive and negative. Probably, hopefully, you know that like charges repel and unlike charges attract. Ben Franklin was the one that gave us the idea of thinking about those charges as positive and negative, and that worked out really well. And he just randomly took one thing and assumed that would be positive, and from that, we managed to get exactly the opposite. So all the stuff we learned about circuits was us imagining positive charges leaving the positive end of a battery, going through a wire, and then coming back in the negative end of the battery. That's what we call conventional current, but it turns out it's completely wrong. In fact, what really happens is negative charges leave the negative end of the battery, go through the wire, through the resistor or light bulb or whatever, and then come back in the positive side. The good news is that that conventional current, i.e. positive charges moving around, doesn't give you any different results than the negative charges going the other way, except in one experiment. And that experiment is called the Hall experiment. And the Hall experiment basically is, you can imagine a wire like this, and you can imagine, for instance, an electric field pointing downward, so that if positive charges are moving from my left to my right this way, then what's going to happen is the electric field is going to cause the positive charges to build up on the bottom edge of the wire. And if you then go and check the voltage from the top edge of the wire to the bottom edge of the wire, you'd find the voltage at the bottom being a little higher. Now, the other alternative is that it's not positive charges going that way. It's actually negative charges going this way. Well, if that's the case, then negative charges going this way are actually going to go in the opposite direction of the electric field. So the electric field pointing down, for instance, push the positive charges down. Now you're going to have negative charges going in the opposite direction. And those negative charges, of course, would force themselves to come down, and you'd have a negative charge on the lower side of the wire. That would result in a lower potential energy or electric potential or electric voltage at the bottom side. You don't really have enough to know about voltage right now, so don't worry too much about it. But unless you're doing an experiment like that where you have an electric field or magnetic field or something like that, and actually I think I was supposed to make a magnetic field, not an electric field. But anyways, if you did, unless you did that, then you're not going to have to worry about the Hall effect. So it's perfectly fine to assume that positive charges are leaving the positive terminal of a battery and then coming back in the negative, even though that's not really what's happening. Okay. So, uh, what happens when you actually do scuff your feet on the carpet is you become a negatively charged object. Then you walk up to a metal doorknob, and you now have sort of this halo of negative charge around you. It's actually stuck to you, but they try to maximize their distance apart because like charges repel. So they're sort of getting on the outside edge of you as far apart from each other as they possibly can. And then when you go to reach for the doorknob, there's a small distance between your fingers and the doorknob. And what happens is that little bit of negative charge on your fingertip compels the negative charges in the doorknob to run away. That metal is a conductor, and electrons are free to move in a conductor. So the negative charges sort of run away from that closest part of the doorknob to your finger and make it look positive to the negative charge. And because it looks positive, the electron says, hey, there's a positive charge over there, and jumps across, and that registers. And if you actually could film it, you'll see it's like a little lightning bolt shooting from your finger to the doorknob. And that's literally basically a negative charge jumping to a positive charge. And that's why you get shocked. Okay. So that's what's happening. That process by which I brought my negatively charged finger close to the doorknob, and the doorknob became sort of polarized, that's polarization of charge. In other words, I didn't change the net charge of the doorknob. I just compelled all the charges to reconfigure themselves so that one side's more negative and the other side's more positive. So it's been polarized but not charged. So I've induced a polarization. Induced is the word that you use there. If, however, I may have had, say, a wire to ground on the other side that I connected, then when I brought my finger near that conducting doorknob, the negative charges on my finger would compel as many negative charges as it could in the doorknob to run down that ground wire and run away. Then I've actually done a net charging of the doorknob. The doorknob will now become positively charged. And in that case, I induced a net charge as opposed to induced a polarity. Okay. So there's a lot of neat little demonstrations about this. In fact, I usually put them all in the links to them from MIT's website, YouTube, all sorts of stuff. There will be a lot of those that I'm going to put in the module for this week. I'll put them in either tonight or tomorrow or something, but you can check out that sort of stuff. So ultimately, what you need to know right now is there's a concept called charge. And of course, you probably already know that that concept of charge includes a negative charge and a positive charge. And we know that the smallest stable unit of negative charge that we can find is the electron. We'll later learn that there's quarks and stuff like that, but they're not really stable. They don't exist for very long. And the smallest level of positive charge is essentially a proton. And that's what's in the nucleus along with neutrons. And neutrons are neutral. Okay. Like charges repel, unlike charges attract. And in fact, the law of attraction and repulsion is called Coulomb's law, but it looks just like gravity. So this is why I had my notepad out, my iPad out, so I could show you exactly what the law of Coulomb looked like. So let me share my screen real quick, and then this is when I'm done with this, I'll let you guys go. So define all boldface terms in chapter 21. Now that's a general rule for this whole course. Every chapter we go over, we're going to have some bold-face terms, and you should always take the time to commit them to memory, even if I don't explicitly say it, because I'm going on the assumption that you guys are reading your book and doing all your examples. And unless it's a specific section that I told you we're going to omit, all of that's fair game. So I want to make sure you do that. But it's very important, obviously, to learn the terms that we're talking about in chapter 21. So I just wanted to give that as a first order thing to mention to you guys. So make sure you do all that. And now I'm going to tell you about Coulomb's law. Now, Coulomb's law is not necessarily the best name. Coulomb sort of had the publication for it before anybody else, but we've found out that, for instance, Ben Franklin did the exact same experiments and came up with the exact same law about the same time as Coulomb. In fact, maybe a little, it seems a little bit earlier than Coulomb did. But at the time, he was in the backwaters of America and traveling back and forth from France on boats and stuff. So the information didn't get out quick enough. So Coulomb got to name it. But we've also found that Cavendish had done the same thing quite a bit of years before Coulomb. But either way, we ultimately have the law, and I'm going to say it's like this. It's the force is equal to some constant times Q1 times Q2, where Q1 and Q2 are the symbols that we use for the two charges, divided by R squared. This is a charge 1. This is charge 2. And this is the distance between the two point charges. Now, notice I just called them charges earlier. I'm trying to point out that they're point charges, 2 point charges. Q1 and Q2. So R is supposed to be the distance between them. By calling them point charges, I didn't have to specify, well, you've actually got to find the center of charge for Q1 and the center of charge for Q2, and then find the distance between them, and that's going to be in there. But by calling it point charge, I didn't have to do that. What I want you to recognize in this is that it looks exactly like Newton's law of gravity, which says F is equal to G M1 M2 over R squared, where this is mass 1 and this is mass 2, and this is the distance between point mass M1 and point mass M2. Again, point masses are the thing to use. We don't necessarily have point masses, but we then have to find the center of mass of those. Now, the big difference here is K is equal to about 8.99 times 10 to the 9th. And that ends up becoming Newton meters squared per Coulomb squared, whereas G is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So you can see that clearly the constant is huge. It's literally 9 billion for the Coulomb force. And in the case of G, it's literally 0.0000000000667 Newton meters squared per kilogram squared. So you can see it's a really, really small number in the case of gravity. In both cases, though, the force acts along the line connecting the two. And in both cases, the attractive force is obviously towards each other. But in the case of gravity, there's no repulsive force. In the case of electricity and magnetism, you can have a repulsive force or a attractive force. And what matters is if the two charges are both positive or both negative, it's going to be a repulsive force. And if the two charges are different, one's positive, one's negative, it's going to be attractive force. But under no circumstances do you put the actual charge, the sign of the charge, into the formula. So I'm going to say, don't put in the signs of the charges. That's just the way that I've taught forever. That's the way I find it most useful. There are times where you could actually put it in, but I just don't find it useful for Coulomb's law. So don't do it. I will say that one, gravity is way weaker and only attractive. Two, they both act along the line connecting the two point particles. Now, of course, that means in the case where you don't have a point particle, that means it extends on a line that connects the two centers of mass in the case of gravity, or the two centers of charge in the case of electricity. Okay. But that's the key point to get out here. Both of them reach infinitely far. There is no distance r such that f is equal to 0. So they call Newton's law of gravity the universal law of gravitation because it reaches across the whole universe. They don't say that for the electric or Coulomb force, specifically because most matter is neutral. We don't necessarily know why. That's an ongoing issue. We have some ideas, we have some hypotheses about why the positive and negative particles about equal each other, so that everything turned out to be essentially neutral. But because of that, it's very rare to have a electric force reach across infinity because so many things are not charged. And because of that, we don't call universal law of Coulomb. We just call it Coulomb's law. Okay. Now we're going to use this in vector form, and I'm going to derive a relationship for Coulomb's law in vector form so that we can actually use integrals to calculate distributions of charges. That's going to be one of the first really hard mathematical problems that we're going to do. But I think this is a pretty good intro to it. So make sure you've read the first few sections of chapter 21 before the next time we meet. I would say read 21:1 to 21:5 for next time. So read subsection 21-1 to 21-5 before our next meeting. And you folks are free to go. I will wait here for the last person to leave in case anybody has any questions, but I do appreciate you coming. I appreciate the feedback I did get. Some of y'all keeping me honest and keeping me from making careless mistakes, or at least telling me after the fact that I made one. So I appreciate that. And like I said, I'll wait for the last person to leave. Don't forget, you've got a practice test available right now. You want to start working on it, and you've got a actual online test that's due Monday night. So get crack-a-lacking. Do you have any questions, John? All right, John might not be here. So, all right, y'all have a good night. Bye bye, everybody. Bye bye. Bye.